Let's talk about the test for concavity and inflection points. Let's say we have a function f, and f is a function that is twice differentiable. That means it has a second derivative over some interval I. Okay, so if this second derivative evaluated at any point x in the interval is greater than 0 for all x inside the interval, then this means that f is concave up on I. Okay? On the other hand, if the second derivative evaluated at x is less than 0 for all x in I, then this means f is concave down on I. So let me highlight this. So positive second derivative means it's concave up. Negative second derivative means it's concave down. One way that you could remember this is positive things make you happy, so you smile, and negative things make you sad or a little frown. So that's kind of how I remember um, this test for concavity that involves the second derivative. All right, let's talk about an inflection point next. So if your function f is continuous at some point x equal to a, and if f changes concavity at that point x equal to a, then this point a, f of a, is called an inflection point. Okay, so let me highlight that real quick. The inflection point is basically the points where the concavity changes. So let me draw a couple pictures off to the side here to give you some idea. Let's say that the function was concave down, and then it hits this point a, f of a, and then it switches to concave up. Then that point a, f of a, that's an inflection point. What's the other situation? Let's say it was concave up, and then it switched to concave down like this. Then again, this point a, f of a, that would be a inflection point as well. So here's a couple of examples where the concavity switches and you have an inflection point. Why don't we take a look at example 3? So in example 3, I have a function f of x equal to x cubed. I don't know why that plus is there. Let's say that this is a minus 6x squared plus 9x plus 30. Okay, we want to determine all intervals where f is concave up and all intervals where f is concave down. We want to list all the inflection points for f. So the first thing I should do is I should calculate the first derivative. So f prime of x is going to be equal to 3x squared minus 12x plus 9. That's going to be the first derivative. And as we know, concavity uses the second derivative. So let me calculate the second derivative, which is the derivative of the first derivative. We're going to get 6x minus 12. Okay, so to find the inflection points, what we're going to do is we're going to set our second derivative equal to 0 and solve it. So when I do that, I'm going to take 6x minus 12, set that equal to 0. One thing I can do is I see I could factor out a 6. So when I factor out a 6, I'm going to get x minus 2 equal to 0. If I divide both sides by 6, I'm going to get x minus 2 is equal to 0, which tells me x is equal to 2. So we may have an inflection point at x equal to 2, but I still need to check the concavity with a couple of test points. So let me draw a little number line here. Here's our number line. We're going to label 2 over here. 2 is my possible inflection point. Let me work with a couple of test points. So if I take f double prime of 0, that's a value that's less than 2. I'm going to get 6 times 0 minus 12. That's equal to negative 12. This is less than 0. That means because it's a negative thing, that means you're concave down, so that's sad. So let me put a little sad face on that side. If I calculate the second derivative, evaluate it at a point bigger than 2, let's say I do it with 3, then I'm going to get 6 times 3 minus 12. That's equal to 18 minus 12, which is 6. That's greater than 0. Positive things make me happy. So then this means that I have a happy face over there. So what's our conclusion? Our conclusion is because it changes sign there, therefore x equal to 2 is an inflection point because the concavity changes at x equal to 2. And you can plug 2 into your original function f to get the y value as well. All right. Okay, everyone. Take care.